Good morning. Very happy to see you here. I'm glad that in the competition over snoozing a bit longer in bed or coming to my session, you chose me. Very flattered. Who am I? I'm Ilias Bergström. I'm a computer scientist in training with a focus always on audiovisual media technology, and I've always worked in this field, really. Currently, I'm working at Elk Audio, mainly as a C++ dev, and I also have a background doing research for about a decade, combining engineering, interaction design, philosophy of science, some academic stuff, anyway. For those of you who don't know Elk Audio, what is it that we do? We've created an embedded Linux operating system, which is specifically for audio, which runs on off-the-shelf system on chips. And the main advantage of it is that you can get 1 millisecond of round-trip audio latency while maintaining high CPU efficiency. And all of this without sacrificing any of the benefits, really, that you get with a standard Linux operating system. So you don't need to customize your code for our platform. We've already presented this a few times over, starting off with a talk and a workshop at ADC 2019, deploying plugins on hardware using Elk Audio OS. So I'm not going to go into more details on that. You can refer to those videos. We have commercial clients for the operating system that I'm not at liberty to mention. Since it's dual license, though, there's also open source users of our OS. For example, the wonderful Nina synthesizer by Melbourne Instruments, which you absolutely have to check out if you haven't seen it. Another product we have is Elk Live. Using this, musicians can play together live over the internet with very low latency. It runs on macOS. It runs on our own bridge device, which uses Elk Audio OS. And we're working on Windows support and an implementation where you can run it as a plugin in your DAW. My colleagues Stefan and Max presented a talk last year going deep into the details of how this works to get the low latency audio over the internet. It was called Networked Low Latency Audio in the Wild, so I'm not going to go into more details on that either. On to the topic for the day. I'm going to talk about software architecture. It's a topic very close to heart. Let's get the definition out of the way. What is software architecture? It's the set of structures needed to reason about the system, which comprise software elements, relations among them, and properties of both. It's from a textbook. All software has an architecture, but not all architectures have been deliberately created. Architecture can often be emergent. Anything that you bash together has an architecture. The question isn't if it has one or not, but, is it fit for purpose? Architecture isn't only about upfront design, though. You don't just sit down, do all the architecture, and then you never think about it again. Some of that is needed, but of course it has to evolve over time. Software always evolves. Software is done when no one's using it, as they say. Same thing with architecture. It's finished when nobody uses your program anymore. I'd say architecture has not been covered very frequently at ADC. Of course, there's topics coming up here and there, but there hasn't been any dedicated treatment. So I figured it's a good idea to give it that treatment in this talk. So with that in mind, I've chosen kind of a broad scope. And my hope is that there should be something for everyone in this talk, from people starting up, junior devs, to seasoned veterans. With that said, there'll be quite a lot of detail in the diagrams during the talk. There won't be time to read every single method signature and understand every single UML diagram. They're there for the big picture and for the YouTube video. I chose to still include them so that, they're part of the talks. There's no paper proceedings like an academic conference. So let's get started. You don't start really with the architecture. You start with gathering requirements and descriptions of what your software is going to do. And that's the input that you use to then start thinking about what architecture is needed. That's where you begin the process. Then I'm going to cover one super important topic on architecture, which is design patterns, low level, architectural level, user experience and UI. And then I'm going to discuss the architectures of the two applications that I'll be covering in detail here. So our two applications, it's a bit funny. The eminent Dave Rowland is talking later today about why you shouldn't write a DAW. So I guess it's a good opportunity to explain why I've come here talking about making two of them. So yeah, also, while I'm talking about DAWs here, it's important to think that many of the patterns and lessons I cover stem from also earlier work in my career with CAD software, 3D animation software, and there's so much in common, but I'm not gonna go into the explicit differences and similarities. Good to keep in mind. Currently, I'll be talking about the two applications, which are first Sushi, which is developed at Elk Audio, and it's Elk's headless live DAW. We've already talked about it at least twice before at ADC, 2019 and 2022. By live DAW, I mean it's more akin to Apple's main stage than, say, Logic. It doesn't really have timelines. That's the main difference. And the main purpose of Sushi is for embedded use in standalone hardware devices and as an audio engine in desktop applications and plugins. It's appeared twice before in our earlier presentations, and it's an integral part of the Elk Audio operating system. So I will not really go into more detail on describing it from a user perspective here. You can refer to the previous talks if you're curious, or come talk to us. What has not been detailed before at ADC is two. I call it a media control workstation. It's my personal passion project. It's like a DAW, but it's intended for all types of media control signals. So MIDI, open sound control, and I plan on adding a bit more like DMX, ArtNet, SACN for light. It uses the JUICE framework. I'll talk a bit more about it since it's not that familiar to you and it's a good basis for the architecture discussion. So how did I come with the idea of making something like this? I've observed that most media creation applications share some common high-level design patterns, also at the user experience level, which forms a sort of genre, and DAWs are smack bam in the middle of that genre. So what I also noticed is that really the major distinguishing feature telling the applications apart was not really all the tools that they have for allowing users to manipulate control signals, but what those control signals send are mapped to control. In audio, they control audio plugins. In character animation, the control signals control an avatar. You get the idea. So I realized I could create a general application which implements all of the patterns of this time-based media software genre, but without hardwiring the control signals to only one particular type of media. And instead, I added some UI elements so that end users can map any control signal sources and destinations in the application to any set of media tools. So creatives are already using sequencer applications to record, play, interpolate. They have control apps to build user interfaces for signals. You see the OG lemur on screen from, what is it now, 16 years ago. They use data flow programs like MaxMSP and Touch Designer to map signals from sources to destinations. And I figured I could make two to allow doing all of this, but integrated in one tool so that all of these activities can also interrelate. So you can combine signals from various sources and send them to several destinations as you see fit. It's a desktop application, and it resembles a DAW and the user experience of using that. So it's not some sort of end-user programming, but it's still for end-user innovation. Wrapping up here about two. End-user innovation is when users adapt and integrate existing tools into a coherent whole in a way that maybe they weren't necessarily made for, but which still fits the purpose of the intention that the user has at the moment. I've traced this back to actually the origin of the modern audio studio. We're in London, the home of Joe Meek. Mixing desks, outboard gear, effects, where you reroute audio freely between all of these and create a setup for the moment, for the song at hand. Holloway Road isn't that far where Joe Meek had his studio. And from then, up to today, okay, we've had the addition of MIDI, we have open source control, we have complex audiovisual instruments now for live projections, light shows, all kinds of live controllers. You get the idea. On to the starting point for making any sort of software. Gathering requirements, limitations, understanding what it's for. You need to plan and design what you do. It's a complex process, a lot of inputs from interaction designers, not the least, from your future users. Of course, a lot of technical details and limitations and constraints. No time to detail all of this here. That's another talk, maybe next year. The outcomes, though, is you get functional requirements, what the software needs to do. You get constraints, sort of design constraints with 0 degrees of freedom, like the platform it has to run on. And you get quality attributes, which is a measurable or testable property of a system that is used to indicate how well that system satisfies the needs of its stakeholders. Things like availability, interoperability, modifiability, performance, security, testability, usability, many more. With that down, very briefly, what are the main requirements for Sushi? It's that it should be fully controllable remotely over remote procedure call APIs. Since it's embedded, it doesn't have a GUI. It should have a dynamically modifiable audio graph, making it an interactive application. It should support the full feature set of a real-time DAW like MainStage, but with this remote user interface. It should support third-party plugins, and the main constraint is that it should perform well in embedded small Linux devices. You know, a Raspberry Pi, an Intel Atom. And of course, it needs to squeeze as much performance as possible out of those devices and support what we do at Elka, a dual kernel Linux environment. More about that in our other talks. So the main requirements for 2, it's quite different. It should implement the main features and user experience pattern for time-based media software. It should allow communicating over multiple control signal protocols and allow bridging between these, so it couldn't have any one of them really hard-coded to its architecture. That's a really important thing to know before you actually start designing the program. And it should allow users to experiment while minimizing risk for error, but not at the expense of limiting creative control. A lot to unpack in that phrase when you're designing the software. And it should be highly visual and interactive without the tedious data entry that you might have in programs where you have to type in a lot of OSC data or where you have to work with data flow diagrams. With the requirements and the design process out of the way in just a few minutes, takes longer than that, I promise, is the design patterns topic. What are they? It's low-level building blocks, general reusable solutions to commonly occurring problems. As you may know, it's something that's been inherited from actual building architecture to the topic of software architecture. You hopefully are familiar with the Gang of Four design patterns book from the 90s. If you're not, still very relevant and current, go look it up. And they're ubiquitous today, really. Like the C++ standard library pretty much implements every single Gang of Four design pattern in some form. Same thing with Juice. I'm pretty sure it implements all the Gang of Four patterns and more. With that said, it's worth just quickly glancing over some of the very basic patterns to build the argument I'm making at this talk. Starting off with the composite pattern, really the basis for any model, I would say. What is a composite? It composes objects into tree structures, representing pot-hole hierarchies, and lets clients of this model treat individual objects and compositions of objects uniformly in the same way. And it abstracts the interface for manipulating and traversing this tree hierarchy. It's what you use to define a model or audio graph in DAWs, for example, and it will also be used in any user interface frameworks that at least I'm aware of for the widget structure. Qt, Juice, the components really are a tree structure. They'll use a composite pattern. As far as I've seen, pretty much everyone does. Moving on to the visitor pattern. This represents an operation to be performed on the element of, for example, a composite structure. And with a visitor, you can define a new operation without changing the classes of the elements that the operation affects. So instead of adding a method to each node in the tree, you have a separate class which contains operations for the different nodes in the tree structure, for example. Good separation of concerns, basically. The visitor pattern is used to display, serialize, and allow structures, editabilities from the user interface. And while the original Gang of Four pattern is kind of verbose and coupled, it has evolved. And there's a very good example by Klaus Igelberger, who proposes a modern visitor version using lambdas, type erasure at CPPCon, I think it was last year, yeah. Moving on to the command pattern. This encapsulates a request or operation as an object, allowing you to parameterize clients with different requests and allowing you to queue or log requests. It's what you use to implement undo-redo in a typical object-oriented application. Meaning, you have a command object and that actually encapsulates an operation and you can queue it and run it asynchronously. You can undo it, you can store that object representing that operation and allowing you to invoke it at any particular time. The observer pattern, it's one of the most commonly used Gang of Four patterns. It defines a one-to-many dependency between objects so that when one changes state, all dependents are notified of the fact. It's what you use so that a user interface, for example, can refresh when it's notified of a change in the model. Finally, out of the Gang of Four, worth mentioning also the flyweight. It allows large numbers of repetitions of equal or similar objects in a model efficiently through sharing. So that's what allows instancing, which I'm sure you've seen in all kinds of creativity software, not the least DAWs, where, for example, in a drawing program, you have one shape, you instantiate it, and then when you change any one instance, you see all of them reflecting that change. That's the flyweight doing its job. My favorite part is that design patterns work best together. So you can have a composite structure, which is altered, serialized, and displayed by visitors. It's modified with commands. It has instance support through flyweights. It's kept in sync using observers. All of this behind a facade, constructed using a factory, and the list goes on. For those of you who did not grow up in the 80s, this is Voltron, a legendary combiner robot, maybe the first that at least Europeans saw. I'm sure the Japanese were way ahead of us. Sort of the Voltron of this community is the juice value tree, which takes what I've been talking about one further step still, combining all of the patterns into a bigger abstraction. Already it's been covered in a session yesterday, and Dave Rowland has given a fantastic talk at ADC 2017, which I warmly recommend. Wrapping up on lower level design patterns, I have a pattern of my own design that I think could be useful to you that I'd like to share. I call it the view context object. So given, for example, a composite pattern model, you have visitors, you have observers, and a visitor might need to store data that's relevant only to itself for future use. You could add fields to the original model, but then they're exposed to every user of it, and it really pollutes the signature. You could duplicate the tree structure so that you have two, one for the visitor, but then keeping these in sync is unnecessarily cumbersome, I'd say. So the solution, I figured, is instead that each node in the model has a hash map into which visitors can store and maintain view context objects, which they later can fetch using a UIDS key, assuming that those implement some simple serialization interface. You can also write them to disk, read them, etc., all without really polluting the API of the nodes in your tree with data that's only relevant to individual visitors. Quite nifty. I only know of it by the name I've given it. If you've seen it elsewhere and it has a different name, please let me know. Otherwise, I claim it with the name view context object. Sushin 2 use many more design patterns, Gang of Four and others, no time to cover them here. I'll be mentioning them in the talk. Definitely look them up if they're not familiar to you. So moving on, from low-level design patterns to the higher level of architectural design patterns. Huge topic, there's loads of literature on it. Still, it's worth showing just 4 module patterns, which are all part of both Sushi and 2. The model view controller stems at least from the 90s, if not earlier. There's many variations. The original is as per the diagram, and it allows separating the internal representations of information from the ways it's presented to and accepted from the user, and how the view and the model interact, which is abstracted into a controller. There's many variations of it over the years. The OG one is what you see in the diagram on the screen. Layered architecture then, the most basic way of really separating concerns. So each layer in the application interacts only with the layer immediately below it, keeping it a bit cleaner. And there's a variation that for observation and notification, you can cross layer boundaries, but you can't for modification. So the presentation can subscribe to changes in the model and get notified of them directly, but any action that the presentation layer needs to invoke on the model has to go through all the layers of the architecture. The last two, server client and broker. So if you have decoupled components in a distributed system that interact over remote procedure calls, then server client is basically what I described, and it's for one-to-one mappings. And if you have like one or many clients and one or many servers, you need a broker between them to decide what RPC invocations go to what server and what results go back to what client. So, final layer of design patterns, just like you have them in software code and you have them in architecture, there's also design patterns in the user interfaces and user experience for applications. Many of these patterns are not specific to DAWs, but together they shape a DAW. And as I mentioned before, other types of software for that matter. So the patterns are really things you recognize from DAWs and just using creative software. You have an editable tree structure for the software's model. You have a property panel per model node, which you see when you select it. You have real-time views, which allow you to directly manipulate the model. For example, if you have a drawing program, you can select the shapes and move them around, or a wave editor in an audio application, the scene view in a 3D program. You have timelines for animating changes to the model. Some software also allow layering automation additively on top of each other. That's not actually something that I've seen in DAWs, but it's very common in character animation software and 3D animation software. So that you record, for example, really complex motion capture data, and then instead of going in and changing every single little node in the tens of thousands of messages that you have from recording motion capture, you can add a modifying layer of a curve on top, which gets added when you actually use the data. Pretty nifty. All of these applications allow writing the data to disk and reading it back into memory. You have undo, redo functionality. You have state storage and recall, which is what we call presets in our industry. Instantiation, so that you can repeat a template across the model, and when it's modified in one place, you see it elsewhere, flyweight. And in addition, time-based media applications allow you usually to connect physical controllers to chosen parameters. They have an end-user programming language, Max for Live, Python. They allow customizing the UI. They expose plugin APIs. A lot more commonly repeated patterns that users are exposed to directly. So, wrapping up on patterns, what is the main advantage? To me, is that they are a vocabulary for reasoning and for communication. The computer couldn't care less if you use patterns or not. It's for us to think about the program and talk about the program with colleagues and peers. Patterns, just like code, are for people. And they make it possible to concisely discuss solutions and reason about them with a common shared vocabulary. And just a final note, they're great for understanding the common tools of our community. The frameworks and libraries that we use all use design patterns. If you know and understand design patterns, you have a much better understanding of the frameworks and libraries that you use, not only at the code level, but at the architecture level. And they interrelate down the layers from user experience to architecture to lower level patterns, but be aware, it's never a one-to-one mapping. You can't just draw a line between them and see which pattern connects to which other pattern down the layer. So moving on, we've looked at design patterns and requirements. Let's look at how Sushi and 2 are put together using these tools. First, let's look at what's common between Sushi and 2. We have classes that acquire resources, and all of those are actually also defined as abstract interfaces. These classes are created and assembled through factories, a gang of 4 pattern. They're passed into any classes which depend on them using dependency injection, a more modern pattern. And all of this makes for highly modular and very easily testable code. We use Google Mock and Google Test for both code bases, and both have quite advanced logging functionality, maybe worth talking about in a different talk here at ADC. Moving on to the architecture then of Sushi. This is the main modules and layers that compose Sushi. It's built to be as modular as possible so that any input and output dependencies are in modules for audio and MIDI. So support can easily be added with wrappers and front ends. We use a model view controller and layered architectural patterns. Sushi can be used as a library, in which case it doesn't need to be controlled over RPC, hence the top layer is dotted. If Sushi runs standalone, the RPC controllers are its main API, its UI, if you will. And finally, the factory and the JSON configurator modules assemble and configure the running instance of Sushi. So they need insight into what the modules composing the running instance are. To instantiate and configure Sushi, then we have an abstract factory interface, and inheriting that, we have a standalone factory, which is when Sushi runs standalone and owns its own front ends. We have a reactive factory, which is when it's embedded inside of, for example, a plugin, meaning it doesn't own its own audio, but it gets its callbacks from the host. And we have an offline factory for when you read audio from a file, process it, and write the output to a file with no real-time audio going on. This is just an outline of the main Sushi model. It has a few more nodes, not many more. Briefly on the design patterns used here. We did not use for this model the composite pattern because really there's not that many different nodes, so it's a bit overkill. We don't really need that tool for this particular case. We did not use the command pattern for the operations on the model. Sushi doesn't currently need undo redo at the engine level. You can implement it on the UI level, if you will. We do use the visitor pattern though, albeit only for serialization. We use the adapter pattern to abstract several audio and MIDI frontends and to abstract several audio processors and internal and external plugin formats. We use observer to notify of changes in the model, and we use abstract factory to construct instances. So a bit about the controller. It's made of a lot of subcontrollers, and it's the external control interface of Sushi. The structure acts as a gang of 4 facade to the more complex underlying structure. It's also a controller in the MVC architecture pattern, and either you invoke the controller directly, if Sushi is a library, or the RPC controllers in turn speak with this controller structure. Messaging is super crucial in applications, especially real-time critical ones like audio software. The main event loop handles regular events in Sushi, like note events, parameter changes, and other tasks that don't block for long. In addition, the messenger has a background worker thread for heavy tasks, like instantiating plugins, loading samples or other large pieces of data, communicating with the disk. And the bulk of communication between the non-real-time parts and the audio threads are done with small real-time events passed over lock-free queues, which I'm sure is familiar to you as audio devs. Our base class for events is event. It's used for the communication in the non-real-time parts of Sushi. There's 3 different types. We have events that can map to real-time events with a conversion. We have events that are for asynchronous processing, and we have events that can be processed immediately, like notes. Events are always passed around like as pointers, so there's no size restriction, And of course, they're never allocated on the audio thread. Finally, our events support registering a completion callback if needed, so that they can notify when they've been executed and if there's any particular outcome of interest. This is interesting. Real-time event is a tagged union of events and commands. So it's real-time safe and is optimized for performance and kept small. It's 32 bytes each real-time event. What's nifty about it is that it works like a base class for a single inheritance level, but it still allows events to be trivially copyable, which if we use virtual inheritance, it wouldn't be possible. It goes against the rule that's typically repeated that you shouldn't inherit from a class that doesn't have a virtual destructor, but with careful use, we get events that can be used in a real-time context and copied byte by byte without expensive constructors and destructors and memory allocations in the heap. The audio engine owns audio processing, contains our audio graph, the lock-free queues to send data to and from the audio threads. And while we do have a richly featured audio graph, I won't detail it more here for lack of time. And probably you've seen another pattern here. This topic has been beautifully covered by Dave Roland here at ADC 2020. Please refer to his talk, it's very much worth seeing. Sushi implements all audio processing, also really the core audio processing that you expect from any DAW, in internal plugins. Some of those internal plugins add crucial functionality. Send return, for example, is implemented as plugins so that users of Sushi can choose if they need send return, or if they don't need it, they can exclude it completely. We also use internal plugins for control voltage support, control signal generation like arpeggiators and step sequencing, audio file streaming input and output. And we also have internal plugins that are good implementations of standard audio tools using the Brickworks library, which Stefano D'Angelo presented last year at ADC. Do watch his talk as well. That's all about Sushi's architecture for now. I'm going to jump over to talking about the architecture of two. I found that open sound controls design is such that pretty much all other control measured protocols that I'm aware of can be translated to and from OSC. So I chose to loosely base the internal architecture of two for the control data on OSC. For you that don't know OSC, it was created by Fried and Wright at SynMat 25 years ago now. It was to augment MIDI for musical performance data, but the use doesn't have to be musical. And it's in very widespread use today, actually, not instead of MIDI, never really meant to compete with MIDI, but rather working alongside MIDI. And arguably, I think it's had its place also when MIDI 2.0 is out for many contexts, not the least end-user innovation. OSC is widely supported. There's many control applications, many DAW supported, some audio plugins supported too, and there's many, many applications for visuals, stage lighting, projection mapping, sensors, etc., which use OSC extensively. Very briefly, since it's so central, I want to show you some example messages here to an imagined subtractive synthesizer. So in the top message, you see the colored bit is what's called the identifying address pattern. After the comma, there's the type tag string, which tells what the type of the payload is. And finally, you have the actual payload. So for example, for the first message that sets the oscillator frequency, it's a float. What's cool about it is that you can read what the purpose of the message is and understand it from just looking at it. So this is what's actually sent down the wire, which means programs don't need to know what it is about. Users can see it and understand. You see, that's the frequency, that's the cutoff, that's the envelope. The full set of OSC messages make up the namespace of any device, in this case, the synthesizer I'm talking about. And each entry in the tree is called a node. Together, they sort of create a tree structure, a file path, if you will. And wherever you see in this structure an F or an I, those are the type tags for a message. Not every node has to have type tag strings. They can just be sort of containers in the path. But if they do have them, then you can send a message with that payload. Enough about OSC. Very briefly, the user-facing features of 2. So typically, users of OSC software have to do quite a lot of tedious typing. There is a protocol that I didn't invent, the OSC query, which automates that. There's a lot of programs that support it, but not all of them do. For any peers that do not support OSC query, 2 automatically builds the namespace of the messages for those devices if they are capable of sending all the messages that they also react to. 2 supports recording, editing, and replaying any messages. I implemented what I saw in motion capture software and figured it's very nifty. You can have an optional layer, which is interpolating, and it's additively added on top of the originally recorded messages. It has presets. You can sequence presets as well, so you can animate over large sets of parameters. And this is perhaps a bit weird. It's not something you would see in a normal DAW. It's what I call a weighted routing matrix, and it's what you use to connect sources and destinations of control data, so that your message is going out, which might be from, I don't know, a sensor, an instrument. You map here so that they, for example, go out to control lights, projected graphics, what have you. 2 gives you a user interface for remote controlling multiple targets. In this view, each column can be a separate device on the network or a device on the same computer. 2 doesn't know. 2 does not require that you first design a UI, unlike, for example, TouchOSC or Linear. But you can design a UI if you want to, and then it has some sort of tools where you can choose what type of widget, if you want an envelope, color picker, that sort of thing. So that gives you an idea of the very basic surface level features of 2, meaning I can go into its internals. It's, again, the overall architecture is a model view controller variant, layered, not strictly. The user interface components can access the model tree, but it's read-only, and they can subscribe to events and access the values of objects to listen to the changes as well, but no modification can happen directly over the UI to the model. The modifications are through command objects, which wrap the actions and allow undo, redo. In 2's case, the model is a composite tree structure of nodes, and you only see a small subset because, given the nature of 2, it has many node types, meaning the composite pattern is a perfect fit for structuring them. In 2's model, there's 2 controllers. One is what I call the engine controller, which is for manipulating the model and dealing with change notifications outwardly and also within the model. When you change one part, it could affect another part. And then I have the messenger, which owns the messaging queues and the event loop for consuming these queues. The 3 main queues for messaging is the main message queue, and then I have incoming and outgoing queues for the user interface. Commands, as I mentioned, is implemented with the command pattern. That way you get undo, redo. Several commands can be scheduled synchronously from the UI action, and also wrapping the consequences of the UI action so that they're batched into a transaction, and then you can undo the whole batch, the initial command and all the consequences, and redo for that matter. Finally, the user interface uses JUICE quite heavily, much more so than for the engine, where I use only really the basic features of JUICE. And since I use JUICE so heavily, really, there's not that much to say about the architecture. I think it's a bit predictable, so it's not worth going into the details here. If you're familiar with JUICE, it will all be vanilla to you. The majority of the components I could mention are based on the JUICE tree view. Suffice to add, 2 has many additional view-specific controller classes. And while the majority of the code of 2 is in the UI, that's really in quantity, not in complexity. So on to some discussion on the topic. I would say DAWs are definitely what I would call quite complex code bases. Ideally, a complex code base should avoid repetition and reuse common patterns. And I think DAWs will always be complex, but that doesn't mean that they need to be also large. A badly thought out code base will definitely be large, even if it isn't complex. If it's complex, even more so. So you get million and million and million plus lines of code, which is maybe not necessary and just makes it more complex to work with it. I've had the luck and misfortune of working with both types of code bases. If you have a really good, deliberate architecture and design, I think it makes for a much more workable code base, even if it's complex, because it reduces the number of concepts in the code and the size of it, and also repetition of concepts with slight variations across, which, if done badly, can drive any dev crazy. Another good point, I've seen it often in any code base that grows in size, that it's quite easy that you get a God class. You know, you start with a nice, solid class. Usually it's a controller and a model view controller relationship, and then over time it grows into a monster. Thousands of lines of code for the single class. It's got disparate responsibilities. Really, all the classes in the model have a reference to this, and it can access all classes in the model. So the all-seeing class. So if you already have a God class in your code, take time to break it apart into smaller single responsibility classes, or at the very least, multiple dedicated controllers. You need to refactor. Speaking of design patterns, the topic of singleton often comes up, so it's worth touching on. It's not that singleton is bad. It's just a tool. But I've seen that very often it's just the wrong tool for the job. I see code bases that use singleton, which could have used a better mechanism and avoided the drawbacks that it has. Very often, probably the most common misuse of singleton I've seen in code is, you know, somebody needs to share a dependency between many classes, but they don't want to pollute the constructor or the interface of that class. So they say, oh, instead of doing dependency injection, I'll just magically spawn the class with singleton in the constructor, for example, or wherever I need it. But that's not really good. It just magically manifests itself inside of the class. You don't really know that it's being used. You can't really alter it when you want to write unit tests so that you can mock it. That has a lot of drawbacks, and in this particular case, there's many more cases like it, just use dependency injection. Pollute the interface, it's fine. If you have too many things passed into the class, that's another code smell, you should just break it up. And here is an important point. There's a balance to strike between power, reusability, and simplicity to use and read your code. Remember, code is for people. You should understand it when you read it. You should understand it easily when you write it. You should be able to talk about it with your peers. That's the whole point. And towards this, design patterns, reusable components, and concepts are the tools we have. They're crucial. I mean, I know I'm stupid compared to the complexity of a computer. I couldn't possibly understand every single thing in a code base. Every time I go into a large code base, I'm relearning it. I go into a corner that I haven't touched for half a year. I don't remember what's there, but I do have the concepts in my head that went into making it, and I can understand what I see in front of me by recognizing these common concepts. I've worked in code bases that are more than 1 million lines. Nobody remembers all of that stuff, you know. That's how you work with it. And of course, you also need to have some careful documentation of your deliberately selected subset of knowledge, which makes the code base easy to understand and get into. So what differences in 2 and Sushi explain the different design choices? Well, 2 has a much more complex model in terms of granularity. It has many more little nodes nested in a much deeper hierarchy. So I use a design pattern for that to make it easier to navigate. 2 also has a user interface, huge difference. Important difference is the emphasis for the application. Sushi emphasizes performance, super low latency, running really performantly and squeezing every cycle out of an embedded CPU. 2 emphasizes flexibility while running on a desktop computer. So completely different, really. And these two things clash. You can't really have both. So you need to deliberately design your architecture based on these constraints, as we did. You're familiar probably with solid and Yagni, you know, the solid principles. If you don't know what that is, look them up. You ain't gonna need it. You use the tools that you actually need to solve the problems you have, not just because you know of them. And these principles really apply to individual methods, to individual lines of code, but also to classes, and they generalize to the architecture. I have no time to talk about these books, but I think if you're gonna start somewhere, start with these 6, and then there's more. If you wanna talk literature, I can talk all day. I love learning, and I love recommending good books. So these are a good beginning for this topic. I hope you wanna know more. You can go to Elk's GitHub for the Sushi repository. You can check out the documentation for additional we have online docs basically for additional information on how to use it. And if you want to give 2 a try, it's at controlmedia.art. I made a new release a couple of weeks ago. For the academics among you, finally, since I was an academic in a previous life, there's a lot of papers on Google Scholar that are relevant to the topics discussed here, and you'll find those if you're interested online. Leaving some time for questions and discussion.